In brief, I'll touch on the ages of the rocks we're looking at, their position in time and in the South African stratigraphy. Stratigraphy is the layers of rocks that progress from oldest to youngest. Where did they form? What they're made up with, and they're mainly those two groups, the Table Mountain group and the Bokkerveld group. We'll talk about this flat, relatively level playing field behind us, up at the foot of the mountains, called Tsitsikamma platform. We'll talk about sea level change, and then we'll talk specifically about what's at Blue Rocks and Salt River, and then what did Nature's Valley look like fairly recently, 4,000 to 5,000 years ago, in what they call the Holocene High Stand, and what we understand about the geology today. So the age of the Earth, as best we know it, is just over 4.6 billion years, 4,660 million years, and goes from the early forms of life down 4.6 billion years ago. The Cape Supergroup started forming about 500 million years ago and went right through to about 350, 360. Okay? And then in this area, we don't have any records of anything in between. But throughout the rest of South Africa, there is. I'll go to that. And then right at the top, the Tsitsikamma platform or terrace formed at about 23 million years during what's called the Miocene. So in the South African picture, here's the Table Mountain group. The blue units are sandstones, and the green units are shales and mudstones. So the Cape Supergroup, which comprises the Table Mountain group at the bottom, Bokkerveld and Witteberg, you can see a lot of sandstone at the bottom, with this shale and this glacial unit called the Pakhuis diamictite in the middle, and that's a very important event. That was about 440 million years ago. This part of southern Africa was actually at about 60 degrees south, and they know this through various magnetic measurements in rocks. So it was really cold, icy, windy, and not very pleasant. And then you go into the Karoo supergroup up there, right up the top. So the Tsitsikamma terrace formed at that age, but because of deformation and the position of the rocks, it was formed on these rocks as they tipped on their side. So where did it form? The Cape Supergroup formed in the Agulhas Sea between 500 and 340 million years ago. That's an extensional subsiding trough that covered from Antarctica through southern part of Africa into South America, and included a continental portion here, included the Falkland Islands and part of the Antarctic Peninsula. So that was a period of extension where the Falklands Plateau was moving southwards relatively. Africa was relatively moving north, and this tensional area, as a result of upwelling in the upper mantle, collected the Cape Supergroup sediments, sandstones, and then mostly shales and mudstones higher up. But no basaltic rocks were intruded as in the Atlantic Ocean. But other than that, it was very similar to the opening of the Atlantic, upwelling in the mantle, but it basically was failed, because already at that stage there was an ocean on this side, the Paleo-Pacific Ocean, which was doing a full-on oceanic separation with volcanoes and basalts coming out. So at that stage, this was starting to really push, started to form a sinking trough here. The Falklands was moving to the north. All these Cape sediments were being compressed and folded and eventually pushed up. And you have this subduction zone on the Paleo-Pacific pushing up, pushing everything that was above it, similar to what you see in the Alps and the Himalayas. The Cape Fold Belt is only this part. Whatever happened to that, there's not a lot of evidence, although there are some rocks of these ages in the eastern foothills of the Andes. So that they know, that they can say is part of the whole process, but that was eventually stripped away and stayed in South America. And at that stage, because of this weight building up here, there was a sagging of the continental crust here, and the Karoo basin started to form. And that's another story. So what we have today, this is a section through from the coastline at George, through the Otaniqua Mountains, the equivalent of the Cedarburg Mountains in that level. We've got the Little Karoo in here, Oudtshoorn, and then the Swartberg Range, and then going off into the Karoo on that side. And this folding pattern, you can see even into the Karoo, going up towards Beaufort West. You start to see these open folds. So this compression was carrying on into the early deposition of the Karoo. So where did these rocks come from? This is an outcrop pattern of the current Cape Fold Belt, which extends for about 1,200 kilometers from Cape Town all the way to between East London and Port Elizabeth. There's a small fragment up south of Durban, which is a subsidiary basin. But we do know that it extends quite far inland. There are boreholes up in this area north of Beaufort West, where they've drilled into Table Mountain sandstone rocks at depth, probably 3,000-4,000 meters down, because that's all under Karoo. And there's even in the Saltpeterkop volcano, which is near Sutherland, which is somewhere up there, there are fragments of Table Mountain sandstone that have come up in that volcano. And that volcano was intruded at 70 million years. It's the best preserved example of volcano in southern Africa. And so they know that in fact the original limit was at least in that. The inland was all granite and gneiss is a deformed granite, much the same stuff, lots of quartz. There were quartzites, lots of quartz. Things like dolomite and the mafic lavas wouldn't have lasted that erosional process to get all the way down here. So only the shallow marine environment is exposed in the Cape Fold Belt. There's the Table Mountain Group sandstones and the Bockerveld shales, and then Witterberg sandstones on top of that, which are relatively shallow water. So the geology, description, stratigraphy is full of names, and they're all full of names related to where their type example areas are. So basically here you see what they call quartz arenite. That's a predominant member. Here you have the glacial member. The Cedarburg Formation is a shale member, very thin, which follows the diamictite, and then another sequence of sandstones going up into the Bockerveld at the top. And this all lies on a basement of Malmesbury Group and Cape Granite. And the Malmesbury Group was deformed in an older event and basically consolidated and intruded by Cape Granite about 555 million years ago. Very extensive number of granite plutons which intrude the Malmesbury Group, which also is a sequence of really deep water sediments and very minor volcanics. So what was the environment in which these sandstones were laid down? We know from that glacial horizon and the paleomagnetic information that showed that this part of the world was about 60 degrees south. It was cold, windy, desolate, icy. This is an image from Iceland, but that's probably very much the style of distribution of these sediments. And just imagine, instead of black sands, those were all white sands, coming off that hinterland of mainly granites and quartzites. As these were being deposited into the sea, it was still a subsiding basin, laid on top of each other as it goes down. So the coastline probably wasn't too different to this. It wasn't as beautiful as that, that's for sure. It was miserable. But you can see the sandy beach, the sandy sort of dune fields, and these braided rivers. This is one of the first times I've ever seen a proper braided river in the mouth of the Groot Rivier. And it's changed again. The river's now out here. But if you try and ignore the greenery in the houses, that's probably fairly similar. But you can imagine sort of icy storms and stuff in the background. Or you can try. So the bedding in these sandstones are mainly these sort of planar beds of sand, cross bedding, laid down in water, large dune ripples in if you go offshore here, you've got the sandbank where the waves are breaking. That's a large dune, ripple. So if we were able to, if that was frozen in time and you were able to cut through it, you'd see a structure like that, as sand is moved over it and off the other side. All by wind. Wind does exactly the same thing. So the dunes at the back here, you'll have that sort of arrangement. And at the Kelders, just east of Hermanus, you get beautiful preserved, cross-bedded, alienated, wind-blown sands, but they're much younger. They're about 20 million years old. They're really good examples. So this is the glacial unit, the Pakhuis. So it's basically formed in an area where the glaciers or ice shelves were pushing off the continent, which was the ice cap, they believed at that stage was somewhere northwest of Calvinia, up where South America was joined on, and that was flowing, pushing southwards into the Cape Basin. And these glaciers, they grind up everything underneath, deposits this fine-grown sandy, and it was mostly sandy, there wasn't a lot of shale involved there. And as the movement stopped, more sandy rocks came in. Of course, icebergs came off and dropped the sands and stuff. So you have a sandy, gravelly layer with a number of large fragments in it. It goes up into the Tsitsikamma formation, which are shales. So it was a very, very still water, and all the fine sediment coming out of this water, which, as you know, when you've seen glacial areas, it's very cloudy and full of fine-grained rock fragments. So the next unit then is the Bokkerveld. You can see very much the same sort of distribution, but largely lying on top of the sandstone. And we're down here. So the major Bokkerveld basins in that area. Strangely enough, the type area is up here in the Cederberg, where it's very well preserved and just is not deformed. And we just have a few slivers here, which are basically infilled. And that's a depiction of the type of fauna that lived on the seafloor in those days. These strange trilobite-like things, various types of mollusks, and these strange, I think they call them crinoids. They have a long stem. They're like I guess an early type of sea fern, but they're actually living. They're probably an early type of coral. They have organisms that lived in it, but all you're left with are the hard shelly pods. So the Bokkerveld group, the only unit which we see in this area is the very lowermost unit, and that's the one that's in contact with the sandstones here. It's the Guido, which is basically mudstone, which is now turned to shale and very much closer to phyllite here. Because really in the shales, you're representing the primary rock. If you drive from Swellendam through to Bredasdorp, there's some beautiful cuttings through Bokkerveld shales there. And in fact, from about Riversdale through to Swellendam, there's some lovely cuttings there of red and orange and brown and yellow shales. And you can see they're all quite often quite deformed, and you'll see a very deep weathering, oxidized layer on top of it. So we get to our part of the world. I found this map in the Breakwater Lodge at the V&A waterfront. I thought it was just fortuitous. This was some years ago. So I took a picture. It was actually a map compiled in 1792. And it had mapped this distinct topographic difference between the mountains at the back, the Longkloof there, they called it, and this Outeniqua area. And there's Naisna, there's Plettenberg Bay, and my interpretation, I think this is the Groot Rivier here. That may be what the Blowkrans was then. But the interesting thing of this is, in fact, it shows the inland rivers flowing west, which in fact we know now they flow east. But you know, they didn't have satellite imagery. They were hard-working guys. So what is the geology here around Nature's Valley? This is now a portion of that map blown up, and it's come out surprisingly clear. It's basically, here's blue rocks right in the middle of this band of Bokkerveld. D stands for Devonian, that's an age, and that's the subscript is for the unit, which is Gedo. It's got these are sandstones. These are all sandstones through to there, and that's Table Mountain. That's Peninsula Group. That's the Table Mountain sandstone, and upper units all the way through to there. A little bit of Bokkerveld, and then once again you've got Table Mountain Group sandstones here. So this is a a steeply overturned isoclinal synform. I say synform because it's a multiple number of synclines and anticlines. And that's been displaced by this fault that comes up through the mouth of the Croatrophere. All those rocks in this area all the way out to the point. You can see they're just a mash. They're a mishmash of mainly quartzite with lots of quartz vein and so on. It's actually a much broader zone than that shows, which goes all the way up the Croatrophere like that. And that's displaced this side down so that that same unit is thrown forwards on that side. So it's also dipping steeply, in fact quite shallowly, but overturned. So that's a 30-degree overturn. And the equivalent of the glacial member, the Pacos, is in fact this thin sliver in here, which you probably will never see. It's interesting that the national road may have been laid on top of it because it was nice and easy to move to grade. But you don't see a lot of evidence on the surface that it may have been under the sea, other than the fact that it's very planar. It slopes very gently from the sea to there. That's at about 260 meters above sea level. This might be about 150. But right here, this is a waterfall. Up here, if you take the Tsitsikamma hiking trail, the first day you walk all the way up here, the Blokran's hut is just behind here. There's a nice picnic spot where this waterfall, current day waterfall, is coming down that cliff face, which was the sea cliff of the ocean that was cutting into there. Now that's not because the sea was at that level. This was much lower down because at that stage, after Gondwana, the continent was still rising. It's called isostatic uplift because most of the continents are granite and they're relatively light compared to the underlying mantle, which is heavy black rocks, and so the continents rise up in that. So as a result of that process, but it sat here for quite a long time. The Miocene ran from 23 to 5.3 million years ago. Okay? So now we changed scale. We've gone from 500 million to 5 million. And there's a lot of stuff happened in between in other parts of the continent. But along this part of the continent, this was then starting to go uplift after the separation of Gondwana, which was 150 to 180 million years ago. So I've drawn a section line through that to hopefully show you what it looks like. And this is courtesy of a young guy who did his master's thesis at Port Elizabeth. There were two of them. One studied the eastern part, east of Tsitsikamma, and this guy studied the western part, looking at the landforms, not really looking at the rocks, but looking at the landforms. But he got some lovely sections in here to describe his landform. And although when you drive along this, it doesn't look that flat, but it actually is very flat. And in that, the Croatrophere and the Stratigraphy have incised. This took advantage of this fault. This one into the Babianskloof unit, which is a much finer grained sandstone. So Salt River probably made that quite easy. And then all of a sudden you drop down again to what's called a Pliocene bench. So this was a younger, so between 5.3 and 2.6 million years, the Earth had moved up again. Don't forget that the sea was receding because of that uplift, and eventually there must have been a point at 5.3 where in fact things sort of stabilized, so the sea could cut away to form this Pliocene bench, and then we have Kilbourne-Strand at sea level down there. So sea level change, I mean this is something in everybody's mind these days, but the short story is it's been going on for a long, long time, and it's part of the greater subject of climate change, global warming, and all the rest of it. And there's very little discussion in the public domain about what happened before. So I'm not even going to go there. I'm going to give you a few snippets. I won't even answer questions, other than maybe be cynical. But there's so much information out there, and I think that anybody who really wants to understand it needs to spend a lot of time. The trouble is you can start on one thing and then you follow that and you end up believing something without actually seeing the whole. It's a huge, and that's the problem with the IPCC. So this actually comes from a poster that the Department of Environment had put up near Hermanus. It actually stands that way up, which showed sea level change from Paco's times, 440 million, how it was below sea level at that stage, and then it rose, and then this is sea level was much lower during the Dwight times, and then all the way up here, breakup of Gondwana, as all these continents were pressed together, they were actually quite high. So this is not actual sea level, it's relative sea level. So relatively it was 300 meters above sea level when Gondwana land broke up. This is like average. And since then, the continent's been trying to rise, but erosion is taking, because that's gravity. Gravity wins in the end. It doesn't matter what you're trying to do to keep things up, gravity will take over. But in Earth time, Earth life, it goes through cycles, because it's also, you have glacial melting, so you have sea level rises because of that. And then the continents also adjust, like Greenland, because there's melting of the ice there, they know already it's starting to rise. But there's 3 kilometers of ice there. Antarctica, there's 4 kilometers of ice and water underneath, below sea level. And they know that if they've got enough detailed measurements that it starts to rise. So, and the whole of northern Canada, northern Europe and stuff is still rebounding after the melting of the glaciers in the last ice age, which was 120,000 years ago. It takes a long time. So what this is preserved in this part of the world that we call the African erosion surface. There was a long period of erosion after Gondwana separation, and this is extremely well preserved all around the country in sort of fragments. And up around Grahamstown, it's well preserved. There's a deep weathering profile, and it's characteristically seen of very deep weathering profiles in the underlying rocks. And in some places now, they still preserve what's called a siltcrete, which is like a silica version of coffee clip or calcrete. And that's the sort of last remnants of all that. Don't forget, you have all sorts of climatic variants. Rainy periods, dry periods, and the water table goes up and down, and that moves things like iron and calcium and silica up to the surface. And so what you see along the road back to Swellendam, you see these little koppies with flat tops. Those are remnants of the African erosion surface. All those sort, and you see the deep light-colored weathering profile below that. So there we are at the Miocene, where we were cutting our terrace, and then the Pliocene, where the sea level went up and down, up and down. So so you have a combination, certainly as you get to these periods, where it becomes more evident, where sea level change is driven by build-up of glaciers and melting. And you get less effect of the isostatic uplift, because this separation away from Africa has a long time, and Africa is virtually stable from that point of view. So now it's just erosion. So what do we see at Nature's Valley? Well, only when we moved to Hermanus, and I became a lot more aware of coastlines and the shapes of mountains and things around coastlines. I realized we've always known about this flat surface. This is the Tsitsikamma terrace, Tsitsikamma platform. This was actually pointed out by this guy who did the masters on the landforms. That this is, in fact, this is the Pliocene terrace that's formed here. And in the background, and then in the foreground, the blue rocks, you've got an even younger one. This is quite possibly a Holocene terrace. This is less than 11,000 years ago, so like yesterday. And this is the one that's being eroded today, and I'll show you some pictures of that. But that, I'll come to why this Pliocene terrace seems to be well preserved here, because it doesn't seem to be well preserved elsewhere along the coast. Now, that's going into the realms of speculation. Geological compilation is all about interpretation. There are facts behind this, but there's lots of other facts as well, which I'm really just making early interpretations, and that's actually been my business for 45 years. That's how it is. So what do you see in these erosion surfaces? This is the Miocene terrace. As you go from the lookout point at the top of Tsitsikamma on the east side, you look back here, you can see this really level surface. And these are all the sandstones of the Table Mountain group in there. And then at the top of Pig's Head, which I only appreciated very recently, there's a conglomerate, pebbles, set in the top of it. And it's a very level surface if anybody's ever been up there. And you can stand up there and you can look out towards the point, and you see that sort of flat area before it goes up to the main platform. That's the Pliocene terrace. So I was very excited to see that. And then the next one, we come to Pliocene high stand. What do we see around here? So there's the Pliocene erosion, and here's the Holocene erosion. All these rocks towards the mouth, they're all they stop at a very certain point. If you look at the distance, they're all much the same level. And then up the valley towards the Tsitsikamma rest camp, you find these strange conglomerates in the side of the wall, and these are very typical of proximal river gravels. These have been run, rocks have fallen down the hill, the river's been in and out, and maybe the sea's been in and out, because what we do know is that 140,000 years ago, the coastline was right out there. Yes. 130 meters below current level, and that was the last major glaciation. All the water was locked up in the ice caps, north and south, and this was an exposed plain. They've done the Council for Geoscience has done a wonderful job mapping all that, because of course this is very important for oil and gas out here, and all that oil and gas is just off that. They've found remnants of the Paleo Breda River, Paleo, what's that one? There's two, the Breda and the Choritz River. They form meandering plains out over this surface. And this is not planed because of erosion. It's actually planed because of deposition. Because this was the edge of the breakup of the Gondwana continent. And as part of that breakup, pulled wedges out of South Africa. And they were, all the faults come along like that. And they come into this. There's a series of uplift blocks and basins which are full of sediment, and that contains all the sediment that make up the oil and gas resources out here. So these rivers were depositing and flowing over a plain, and they actually know quite well what it looked like, because at the caves of Blombos, Pinnacle and De Kelders, they have evidence there of occupation in the Middle Stone Age, 70 to 90,000 years ago, of what people were eating and what they were hunting. And they were hunting animals and finding plants which are actually very similar to just inland. The plants are very similar to the inland fynbos areas in the Southern Cape here. But the animals, there was no known existence of those. The bones are there. And recently, here at Hartenbos, they found in the most recent rock evidence of, there's all sorts of animal, antelope footprints, giraffe, rhinoceros, and now elephant footprints that are preserved in those rocks. They always thought they were eroded out tree stumps in those, but they're not, because they tried to analyze the patterns. But these are in fact more like an elephant track. So that was the picture 140,000 years ago during the last major ice age. So we're here. So what happened to the stratigraphy and the Salt River and maybe the below crust? Where did they go? Because they're actually quite, the stratigraphy is, in fact, you can trace it back into the mountains. It looks like it's always been there, but the Salt River is much younger. It doesn't have that extreme profile, but it was in existence at this time, because we'll see when we get to what's in Salt River. There's such a lot of stuff written on that Agulhas Bank now, on the paleo environments, Haley Cawthron, Chancellor for Geoscience. So this is what happened to sea level the last 200,000 years. So this was that glacial period, 140,000 years. Went up to about 8 meters above sea level, up and down, up and down. The middle Stone Age is about there. So there was a lot of exposed land. It makes you wonder, some of these sort of shell middens and things around here, have they ever been properly excavated? And then the last glacial maximum was in fact about 20,000 years ago. And also the sea level got pretty low there as well. So there's a lot of evidence in those caves of what people were eating and living off. The Pinnacle Point cave is quite well exposed, or quite well described, but not well exposed, because they tried to protect it. But the Kelders is very well documented. So sea level change. So the paradigm is that sea level change is a certain consequence of global warming. So this is as close as I'll get to conjecture. But ice age cycles over the past 900,000 years have seen sea level fluctuations between 130 meters below and 8 meters above. Present meltback of all remaining ice on Earth would create between 58 and 65 meters of sea level rise. So your house here would not be safe. But that's unlikely to occur, because the last time was that the late Cretaceous, 65 million years ago. That's just after a breakup, or before the break, just halfway through since the breakup of Gondwana, when the whole continental configuration was very different. So as a result, ocean currents were not circulating in that basin, and also there was a transfer of ocean currents, particularly the Southern Ocean from the Pacific across the Atlantic and the Indian. And wind systems, which oceans drive the wind systems as well. And also this magical thing, the Milankovitch cycles, were not set in place. So Haley's view is that based on study of past fluctuations from a geological perspective, in the next 200 years, global sea level could be expected to rise between 0.9 and 1.8 meters. And 11 meters above present in the next 40,000 years. Now that's based on her mapping and understanding of the cycle of movement and what's driven seashore movement as she's examined on the Agulhas Bank and just onshore in the Bredasdorp area. There's lots of evidence there. So it's a natural process. And she agreed, although human impact may enhance or accelerate the rate of climate change and sea level change is largely a natural process. So what are these Milankovitch cycles? And I think this throws in now a whole bunch of different parameters, which you can remember. This is the tilt, which is sort of why we have the topic of Capricorn, the topic of Cancer, where they are. That changes on about a 40-odd thousand year cycle. Then you have the axial precession. In other words, the axis, doesn't matter which way it's pointing, is not in one place. It actually precesses like that. And I think they found evidence of this from why the pyramids and the Sphinx and various other ancient things they were actually pointing at something which was in a different place then, and that's because of axial precession. And then change then the eccentricity of the Earth's orbit. It's not a circle around the sun, it's actually an ellipse. But that ellipse oscillates as well. They reckon on a 100,000 year cycle, and then on top of that, we've got an 11 year and 206 year cycle of solar variability, sunspot activities. Can you imagine the situation where all of these things for a certain part of the globe were all closely aligned to the sun? That part, you would have massive warming. And look at the periods though. I mean, it's only in hundreds of thousands of years. So these things, and then as it's all complete the other way, you could go into a massive ice age. And it's these things which have had a large part of major ice ages in the past. I'm talking like the Puckos and the Dwika and similar ones. They are related more to these than to anything else. So what's at Blue Rocks? Well, I told you all about the rocks, what they are, but interesting to look at what you see here. So close in at Blue Rocks, the top here, this is the Pliocene terrace. In the background, you can see the Miocene and the Pliocene terrace. Okay? And that's I think down at Cuba. And here you see the Holocene high stand. That's a platform which is eroded here. And here's the current terrace being eroded. So it gives you a very good example of how these, because this is in the active wave wash zone. Okay? But that's coming off quite a steep drop off here. So there's obviously faulting offshore. And so below this, there will be other terraces, which is similar to what Haley's found on the Agulhas Bank. But this is quite a nice example, what they call a notch, an erosional notch. There's one there, and there's one here. So there's two levels of sea level just in Blue Rocks. Plus the Holocene one, which is about, well, less than 11,000. So as I was trying to describe on the outcrops there, this is not Blue Rocks. And it could never have looked like this. Doesn't matter what it is. But basically here I was trying to describe, you get this bedding. That's the original bedding, and it's folded, and you get these cleavages formed to accommodate the compression. Everything starts to slide out of the way. As you compress, things slide out of the way. And that's what it looks like in outcrop. Not too different to Blue Rocks, but in a descriptive sense, that's what you'd see. And those cleavages run subparallel to the axial plane trace. In other words, the center part of the fold.
This is your deck of cards.
Yeah, that's a stack of cards. If you take a stack and hold it like that, stick your finger in the end, you get that. If you were to draw a line on the side and you push your finger in the end of the stack, you'll see it fold. So this is now open to interpretation. There's the Crotrophia fault coming out there, and the whole of that front of the point, and all along there, those rocks are completely shattered by movement along that, because they're very hard, they're very brittle, very competent rocks, so they broke up. And I think it's quite likely that here in Cinque Bay here, that there's probably faults bounding that. And those may be part of the breakup, the Gondwana breakup faults. There'd have to be a lot of work done to try and date those, but it's possible to do that. And why do the rocks stop there and they don't go all the way along the beach? Or maybe there's another fault there. And then what's at Salt River? This really only came to me fairly recently, that in the Pleistocene, 2.5 million years ago, sea level was a lot lower. That's glacial times, to about 1.8 million. So these rivers would have drained right out onto the edge of this part of the Agulhas Bank. But they would have cut down from the Pliocene level. So Salt River and the Crotrophia cut down. They cut through this, but then this is a fault that I believe extends from Cinque Bay, and I think that defines the boundary of that ridge on that side. And if you climb up, when you climb out on this path here, where that path, those steps are being put in, there's a very broken, fractured rocks, and that may represent a fault breccia that lies there. So this is, I should have put a big question mark in there, but kind of makes sense to me.
Sorry, John, can I ask something? If you go just around the corner, there's Pebble Beach, you know, those pebbles, where does that fit in?
Okay. Now that's interesting, because then people say, wow, look at these pebbles. Why? Those pebbles probably came off the top of that, the Miocene terrace. They were all because those are all sandstone. And they were probably being generated all the way back from the Miocene sea cliff, which is all in sandstone. All the sandstones were making pebbles as the sea receded, or as it eroded in. It broke up lots of rock. And that's a beautiful washing machine erosional process. Rivers make similar things, but they're always very channelized. But I believe these are largely derived from erosion on that Miocene terrace. And they've been sort of brought back. And in places around on that surface, you'll see pebble conglomerates, the smaller ones usually. And on top of Pig's Head, I showed some remnant of those pebbles that were left there from the Pliocene erosion. So during the Holocene high stand, which was about 4,000 to 5,000 years ago, and this is an expression that the geomorphological ocean scientists use, high stand, low stand. It got me to thinking as to why Nature's Valley? Why is it why is this little pocket of beauty? But of course it's all Bockerfeld shale, the softest unit in this whole neighbourhood. So they've got a big fault this side that forms that buttress, because these are sandstones here. The shale is up there where the pass goes up. So at the Holocene high stand and various times in between or since, this has been a little soft pocket to be eroding here. So the steep hill at the back here is actually also a sea cliff. It's the Holocene sea cliff. And that goes all the way around here, and then as you get to past Salt River, back into quite steep stuff, and then you're back into quartzites around this side of the hill. So that's what I think. So what happens next? So what do we see? So during this high stand, along the road to the campsite, you see this unsorted conglomerates and sandstone wedges, sandy beach. This is not even a stone, it's actually still fairly soft. You can scratch with your finger. Two different beaches. All river deposit, beach or river deposit. Possibly sandbars in the river. These very proximal conglomerates, although there's a layer there, you can see slightly rounder. Maybe the river was in fact rolling these pebbles on the surface. Lots of work to do there. So in plan basis, this is what at first look. So you can see the high stand terrace here. We see it in these rocky outcrops out here. We see these conglomerates just up the pass here and then the road there. And that's the embayment up against, cut into shale at the back of Nature's Valley. And you've got that stream has probably been around a while, and there was that stream there. So when they were doing the drilling for the sewage plant, 2008, they drilled a lot. These were boreholes they drilled all over. And from that came the identification of this patch of clay up here where people must not put septic tanks, they have to put conservancy tanks. And I didn't see in the report any description as to why that would be, but my interpretation is such, and I'll show you in the next slide, that you've got a fossil dune here and also a shale ridge. And I know that because my house is there, and in sinking the foundations and the house next door, Wagner's place, and all along, I think probably all along St. George's here, the foundations go into shale. Mm-hmm. Whereas you come this side, and there's thick sand all the way along here, and a little bit in this area here. So this is what I think we've seen from that. So this would be a cross section. It's quite expanded, so that's 15 meters up, 15 meters down. So this would be the Holocene high stand, eroding this. This would have been an earlier sea level, cutting a ledge here. We don't really have enough information. Comes up to that level, And then just weathering of the eroded material on its surface probably generated a lot of clay from the shady rocks. So that clay band sits right there where that stream bed comes off the mountain, runs along there, runs below St. George's Avenue, crosses the road at Heather Street, goes through the backpackers and out along St. Patrick's into the water pipe at the end of St. Patrick's. So in summary, what we have today, we've got shale all the way up to there, sandstones all the way through there, the Holocene high stand embayment, we've got the Croat-Rivier fault, we've got these remnants of the high stand there, and there. We've got the Pliocene high stand at Pig's Head. We've got the shale ridge, which is not well defined, but it seems it lies just on the inland site of this paleo dune. So if you can imagine that was a shoreline, you've got the older equivalent of this beach. Now in Heather Street there's a house where they've cut into that dune to make a driveway, and there's an older looking sand in here. It's sort of not consolidated, it's quite soft, but it's not like this, not like these beach sands. This is the recent to modern beach sand dune called. This is active. This would be called fossil. So there's a whole sort of story that can be pulled together here, and I think with a lot more work in a number of patches, we could have a lovely expose of a number of features here, from the older rocks to very younger rocks, early younger erosional terraces. And I think that when you look at the point there, you can see the two main ones, and then you can kind of imagine the one low level next to the sea. There's a point sticks up, but there could be 2 or 3 other levels in there, which in themselves would have cut back up into the Croat-Rivier. So up the Croat-Rivier, you may find other terrace levels that are preserved, stuck on the side of the valley. Right, here we are.
Sure.